rehearsal of the main session. A reminder that there's at 5 o'clock there's a special lecture from Mike Berry. But before then, we have Mark Dennis from the University of Bristol designing fibred knots in optical fields.
Okay, so thank you. So this is going to be a talk which is not about fundamental physics. This is going to be a talk about how we've applied some pure knot theory to a problem in laser physics. And so there are going to be a lot of assumptions and approximations about the physical model that I'm not going to go into because of time, but please ask me if you have some questions. So this is mainly work with my former PhD student, Robert King, but there will be experiments, if we get that far, at the end, which were performed by my colleagues in the University of Glasgow. So the main idea is that light, such as this laser spot here, can be represented by a function, a complex function of space. We've seen several examples of complex functions of space already today in physical systems, such as the superfluid order parameter in a superfluid turbulent system, and the mathematical idea of this structure being just a function from the three-dimensional space to the complex numbers is the same. The big difference is the physics that I'll be talking about is linear, not nonlinear. Because, of course, as light propagates through empty space, we can just add waves together directly. So I won't be worrying so much about the nonlinear dynamics. Instead, how can we create knots and links with linear interference? So, of course, most people here will be familiar with the idea that plane waves, if I look at the surfaces of constant phase, the argument of the complex number are these planes propagated with the planes perpendicular to the direction of the propagation of a wave. And in optics, just as in superfluids, we're not restricted just to having waves with this sort of topology. We can also have the surfaces of constant phase spiraling around lines, which we call optical vortices, just like superfluid vortices. And these places are where you can see all of the phases come together on these lines, and mathematically that's possible because these are the zeros, the nodal lines of the complex scalar functions filling space. So, but I'm not going to be talking about these lines being straight. I'm wondering about how it's possible to bend these lines around, curve them, and close them up into the form of different knots and links. And the question that I'm going to answer is, can we create laser beams with these zero lines, these nodal lines, these optical vortices that have topologies of certain knots and links? So there's a lot of interest in these sorts of questions in optics, mainly from a mathematical viewpoint. Holograms act as initial conditions for light beams. So if I have, this is approximately a Gaussian profile in what we normally refer to as X and Y, the transverse plane, and then these beams propagate in the Z direction, I can illuminate a hologram which effectively has is a complex function of X and Y, and this multiplies this function, which then propagates according to Maxwell's equations. And because I've got this zero in the middle, this zero remains on the axis, the XY origin of this beam as it propagates. And you can see that the phases, the arguments will increase from 0 to 2 pi going around. So this is how one puts an optical vortex onto a laser beam. And so as these beams propagate through space, they have these helicoidal wavefronts, as I showed before. And there's a lot of interest in optical engineering at the moment about this question, because if you can embed these topological numbers on the axis of beams, perhaps this can be a way of increasing the amount of data that you can transfer by lasers. So the New Scientist had a story about this, twisted light. It's fast, it's furious, and perfect for speaking to aliens. The idea that maybe aliens are actually communicating to us with beams of this type. And just recently it received some media attention. There was a public demonstration of sending helical radio waves across the Grand Canal in Venice. Mathematically, I'm interested, as I said, in linear waves, and the waves satisfy it's actually the 2 + 1 Schrödinger equation, but this is an approximation of Maxwell's equation. So psi is our complex function of position, and all the beams I'll show you are functions, are solutions of this so-called paraxial wave equation. It's just like the two-dimensional Schrödinger equation, where the z direction as the beam propagates, it's like time in the quantum mechanical picture. And the natural basis that we usually consider with these things is the basis of so-called Laguerre-Gaussian modes. So these are Gaussian wave packets that are multiplied by a polar, or e to the il phi, times a Laguerre polynomial that has certain nice properties when it evolves under this equation. So for example, if we have one of these vortex beams, this is what it looks like shortly after the hologram, and as it propagates, the phases swirl around, but the zero remains on the axis of the beam. A higher order one, so 2, I've got a 4 pi change around the axis, and this Laguerre polynomial has got 1 radial 0, but this is not stable to perturbation. If I just add a little bit of some sort of 0, 0 Gaussian, this double charge thing splits up into a single a pair of singly charged 2 pi quantized vortex lines here, and then there are these 4 vortex lines that come from this line discontinuity here. So these are the sorts of beams that I'll be thinking about when I consider my superpositions. So the question is, can we make optical, or can we optically knot vortices by linear interference? So one of the rules of thumb in physics is, of course, anything that is not forbidden is allowed, but that doesn't tell you how to do it. So we expect that we should be able to do it, but how do we do it? That's the question. Now, some older work that I did with Michael Berry just over 10 years ago, we found actually solutions of these equations that had knots. Here's a trefoil knot, but they were threaded through by some extra vortex lines. So these were torus. This was a scheme that was based on some sort of perturbation of a degenerate configuration, which gave torus knots that were always threaded. So the question is, can we make non-threaded knots, sort of isolated knots, and non-torus knots? And to do this, we need some knot theory accommodating the fact that we're not just taking a piece of string and tying it into a knot. We're taking a full 3-dimensional function of position and creating a nodal line that has a knot in it. So what we're effectively doing is knotting a field. And this follows Kelvin's knotted vortex conjecture in the ether. Of course, Kelvin worked with Tate, who created some of the earliest knot tables, and you can see this is Tate's first 7 orders of knottiness. Here's the trefoil knot, figure 8 knot, the 2 5-crossing knots, and so on. So, because I'm talking about complex functions, the knots that I'm interested in mathematically are the so-called fibred knots. The knots which, if I remove the knot from 3-dimensional space, I can create these surfaces of constant phase that fiber over the circle. That is to say, as my phase evolves, these wavefronts effectively fill all of space, and as they fill all of space, they never cross, and there are no points that are missed out. And that's not possible for all knots. It's possible for this class of fibred knots. And this, I believe, should be the case whenever you're talking about knots in a complex scalar function of position, such as the superfluid vortices as well. These all ought to be fibred knots, assuming they're not threaded by other objects. It turns out that torus knots are all fibred knots. So there should be no problem in making the torus knots. The figure 8 knot is also fibred, but the other 5-crossing knot, the 3-twist knot 5-2, is not fibred. So there ought to be no possible way of making a complex scalar function of position, whatever wave equation or whatever it satisfies, which has this knot just from a topological, this topological requirement to be fibred. So fibred knots were studied quite a lot, and in particular, Milnor in the 1960s related this to singularities in high-dimensional spaces. And effectively, what that theory led to was a theory of constructing knots as functions of zeros of functions of space, complex scalar fields, via polynomials in two complex variables, which may be obvious to some of the mathematicians in the audience, but I'll go through it in a bit of detail for the physicists, maybe a bit less obvious. And in particular, what this approach that I'll describe does, which follows the work of Perron and Rudolph, who used a similar approach to generate the figure-8 knot, is a way of actually constructing functions of space with knotted zero lines that are knots by making them follow not fibred knots, but instead fibred braids. So this is the trick to attack the problem of how to make a function of space which has a knotted zero line. So the idea is we construct a complex polynomial whose variable is u, just a single complex variable in the Argand plane, and this polynomial has n roots, and these roots are parameterized by some real variable h. So, of course, the polynomial, I can just use the fundamental theorem of algebra to create this polynomial where in a variable u depends on these roots which are functions of h. And so, for example, I can have my three roots executing this Lemniscate path. And so in time, what you can think of is these things are tracing out a pigtail braid in time being the third dimension coming out of the board. So this would be just like a pigtail braid in hair. And this is an explicit function, this polynomial function, to give us this idea of a fibred braid. And then what we employ is one of the most famous theorems in knot theory. Oh, sorry, this is explicitly these functions of h in order to get this particular Lemniscate shape. So we employ, thank you, Alexander's theorem, which tells us that a knot is a panoramic view of a braid. So this is a panoramic view of my home city of Bristol and a braid. And that was me taking that picture. And you can see this idea that this panoramic view of the knot is what I get by joining the two ends of this torus together. So mathematically, what is that? Well, I was just looking at a double helix braid, a pair of roots here. So there's e to the I h on 2. So as this time evolves, this h, they wind around each other. And then this trick is to take my polynomial e to the I h on n and replace it with some extra variable v to the m, where n is the number of strands and m is the number of repeats I want before I close up the strands. And this gives me a polynomial in u and v, and this is exactly the polynomial that Milnor talks about in his book. Then I replace u and v with functions of x, y, and z. These functions, r squared is x squared plus y squared plus z squared. This is just usual stereographic projection from the three-sphere into three-dimensional real space. And lo and behold, this gives me a complex function of x, y, and z with a knotted nodal lining. But this idea of braids can now be extended. So that pigtail braid I was showing you before, so this is this like braided hair, now doing this same trick of replacing where this is the number of strands, 3 strands, and this is the number of repeats. I've chosen to repeat it twice. But because this trigonometry now involves both cos and sine, I'm not just involving v, I also have the conjugate of v. So my two-variable polynomial doesn't just involve v, it involves the conjugate as well as u. This is the function that embeds this pigtail braid into this sort of braid space. But as I do this transformation into x, y, and z, I now get a function of x, y, and z with a knot along a line, and this is the figure-8 knot. So this is a way of constructing these functions to find these knots. Now it's not, this approach to constructing knots naturally lends itself to thinking about families of knots that aren't quite usual. I'm thinking about families of knots that come from braids where I specify the number of strands, the number of repeats, and in this particular class that I've been looking at, the number of loops. So it's a sort of iterated lemniscate, one loop. I just have n strands repeating m times as I go around. That's the torus knots and links. But this figure 8 with 2 loops gives this particular family as I increase the number of strands and as I increase the number of repeats. And these blobs are just because there are no standard conformations of knots more than 10 crossings. I can keep on going, and you can see now I get several more of the fibered knots in the knot table, and links as well. And there are lots of patterns in these sorts of ways of building up that are a little bit like Slavik Jablan's schemes of trying to construct these various knot families from thinking about braid representations. I won't talk about it, but you can also make satellite knots by effectively iterating this construction by adding epicycles and so forth. So what we have is we found a complex polynomial in x, y, and z with a knotted nodal line. That's what I've told you how to do, and it's a hopefully useful scheme. Now, how to make this relevant to optics? In the symmetry plane z equals 0, this polynomial x, y, and z I can think of as a function in x and y. Here's a complex, and this is the phases, and you can see what I've effectively done is sliced this bagel through the middle, and the 6 places this crosses are these 6 vortices here. But because I'm interested in this particular linear equation, which is first order in z, I can just propagate it. I can propagate this polynomial in x and y to give me another polynomial in x, y, and z. As it propagates, lo and behold, it gives me the same knot, although it's not the same polynomial. I've got some ideas on how to try and prove it, but I have been unable to prove that as a theorem. All I can say is that it always seems to work, and if it doesn't work, I know all these sorts of tweaks to make it work. Right. So the resulting polynomial wave function has a fibered knot. So I made a braid, it turned into a knot, and then I propagated it. So here are some other examples. Here are the Borromean rings. Here's the 818 Turk's head knot. Here's, well, the Milnor polynomial giving us the 7-7. And I will just quickly flick through the details to show how we actually embed these into laser beams. We can do it so long as we're careful. Working with superpositions of these Laguerre Gaussian beams I showed you, and a laser, hologram, and then imaging with a CCD. So this is now, the CCD is moving through this line here, measuring intensity and phase in each plane. And here are these vortices going through their little dance. You join the dots in the computer, and this was a hop link. This was the trefoil knot. Again, you can see it's sort of threefold symmetric, going through their dance. And there it is. And here was the cinquefoil knot. But the figure 8 knot with this rather more complicated spectrum was rather more difficult and not able to do in experiments. I'll just, and finally for Lou, I will show that this was a scheme, given we've been able to tie laser beams in knots, we can work with entangled photons, so we were able to study entangled tangles with a pair of photons each in this knotted configuration as a way of using the topology to try and count the photon correlations. It wasn't incredibly revealing, but it did enable us to write a paper called Entangled Tangles. So just to summarize, so these Milnor maps are complex scalar fields with fibered knots as their nodal lines, and they can be constructed using braids. And there's a unique polynomial solution to the practical wave equation which agrees with the Milnor polynomial in the symmetry plane, and it has a knotted nodal line. By monkeying around a bit, we can experimentally realize these knotted beams. And one of the things that I would hope, that, that if you've got a physical system you're trying to do knots, I'd be interested to know whether this Milnor polynomial construction might be useful to create knots in other systems such as solitons, fluid vortices, or liquid crystals. So thank you very much.
Time for one quick question.
Well, mathematically it is interesting, but why is it interesting physically? All this.
So the particular interest in, as far as the lasers was concerned, is that we have it was more of a demonstration of the actual ability that really the very sensitive control that we can exert over the over these vortices. I mean, they're the most sensitive features of the interference, because where exactly it's 0 rather than just dark is actually quite a hard thing to get right. And so being able to get this knotting just right was seen as an achievement by my experimental colleagues. As I said, there's not necessarily anything fundamental in here.
Okay, I think we better, if we better have time to take a breather before the talk, I think maybe we better leave any more questions to a short 8-minute break before Mike Berry's talk. Let's thank all the speakers again.